Okay, continuing with the digital signal processing, today we'll handle various methods which are less obvious than the things that followed from simple properties of Fourier transform. And they are at the same time both more powerful and more dangerous than the linear processing methods, because really with things like window functioning, you cannot get it wrong. It is a method that's been tried and tested and used for literally hundreds of years by now in just about every field of digital signal processing. But the methods I'll be talking about today are, on the one hand, specific to spectroscopy and even specific to NMR and EPR, and on the other, don't actually have that ample safety margin that the methods listed in the previous lecture did. The first thing that people often encounter in practice when they do spectral processing is the fact that an NMR spectrum is of course complex. It has a real and imaginary part, but if you have a paper from 1960s and you are relying on a printed spectrum and maybe digitizing it from the page, and somebody didn't bother to face it properly in that page, you're in trouble because you don't actually have the imaginary part of the spectrum. Or the part hasn't been recorded to start with, or has been lost, and the task of phasing becomes seemingly impossible because the imaginary part is missing. Fortunately, the properties of linear time invariant system actually allow you to reconstruct the imaginary part of the signal from its real part, and it is a highly instructive exercise in NMR and EPR in general to give a, well, for us really to give a proper derivation of where it is and where it's coming from. One property of LTI systems that we haven't mentioned in the derivation of Fourier transform was causality. And causality simply means that the consequence cannot precede the cause. And so if we have a response function of our LTI system to some external signal, the response cannot actually come before the signal. And so if the system has a timeline and some pulse was applied to it, let's say a delta function, and then the system responds to that pulse, gives us some signal out, there cannot possibly be a signal preceding this because there was no perturbation. What this means in practice is the response signal that we've got f of t to a perturbation that has arrived at time 0 must vanish for t less than 0. So f of t is 0 for t that is less than 0. And so the response should not change if we multiply it by what's called a Heaviside step function. Maybe I should make a step in the opposite direction here, like this. So this is h of t, and it is defined as a function that is 0 for t less than 0, and 1 for t greater than 0. So strict definition is h of t, the Heaviside step function, is 0 for t less than 0, 1 for t greater than 0, and it is undefined at the 0 position, although of course you know that Fourier series often converge to midpoints for this continuous function, so that can be used to define it. And so our f of t, if we multiply it by a constant, so just multiply it by 1 everywhere, and this will be our c of t, and c of t will just be 1 everywhere, so we multiply by this. This product should be the same as if we multiplied by the Heaviside step function, t, h of t. You see, it has been 0 here anyway, so it doesn't matter whether we multiply it by 1 or by 0, nothing changes. So we've got this relation then in the time domain. This is our response. This is a constant, it's equal to 1 everywhere. This is our same response, and this is a Heaviside function. It's defined as I defined it. But we know that there is a correspondence between the time domain and the frequency domain, And you remember from the previous lecture I demonstrated you that multiplication in the time domain is equivalent to convolution in the frequency domain. And so if we take Fourier transforms of this, they must instead be related by convolution. So f of omega, our spectrum, convolution with c of omega, the Fourier transform of a constant, we'll get to a moment to what that equals to, must be the same as f of omega convolution with the Fourier transform of the Heaviside step function. So Fourier transform of our system response is just the spectrum, the NMR spectrum. But let us now find out what are the Fourier transforms of a constant and what is a Fourier transform of the Heaviside step function. Right, so for a constant, from just the definition of Fourier transform, c of omega is 1 over root 2 pi integral from minus infinity to infinity, constant c of t times e minus I omega t. Constant is just equal to 1, so that's 1 over root 2 pi integral from minus infinity to infinity e minus I omega t. Who remembers what this equals to from the previous lectures? Delta functions. Yeah, you've got handouts, so you can actually check. So it's a textbook integral, and it's equal to root 2 pi delta of omega. Now, one thing that I will not derive, because it is really a very subtle matter, as Fourier transforms of discontinuous functions always are, is the Fourier transform of the Heaviside function. Naive ways of calculating this Fourier transform always lead to incorrect results. One has to take extreme care whilst doing that, and extreme care means at least 3 pages of reasoning, with contour integration in the complex plane and things like that. So what I will simply do, this is not a lecture course in the theory of generalized functions, is I will give you that Fourier transform. So h omega is the integral from minus infinity to infinity 1 over root 2 pi h of t e minus I omega t dt. And skipping the very, very lengthy derivation here happens to be equal to 1 over root 2 pi delta of omega minus I over omega. Okay, so what we now know is we know both c of omega and we know h of omega. Why don't we substitute those expressions there and see what happens? Okay, root 2 pi f of omega, convolution delta of omega is f of omega, convolution 1 over root 2 pi here, delta of omega minus I over omega. Right, convolution with the delta function is equal to the function itself, so this is just root 2 pi f of omega. Then the same here, it's 1 over root 2 pi f of omega minus 1 over root 2 pi I f. Let's put it this way, I over 2 pi f of omega convolution with 1 over omega. Right, we can cancel a few things here and there, and what happens after we simplify this expression is it turns out that f of omega is 1 over pi f of omega convolution 1 over omega. This doesn't look particularly useful because it simply gives us f of omega in terms of itself, but look at this I in here. If we took the real part of f of omega, it would become the imaginary part. So it would seem that this transformation at least mixes the real with the imaginary. So why don't we write the real and the imaginary part of it separately, and then see what happens. Just push it down. Let's first write it in the integral form. So f of omega from the definition of convolution is 1 over I. 5 integral minus infinity to infinity f of the integration variable mu divided by mu minus omega d. Yeah? And then let's take the real and the imaginary part of it. F, real part, omega, will be 1 over pi. But because we had the I, it has swapped the real and the imaginary part and put a minus sign in front of the imaginary part. So what we will have is integral from minus infinity to infinity f imaginary of omega over mu minus omega. And similarly for the imaginary part, omega is minus 1 over pi integral from minus infinity to infinity f real of omega mu here, d mu, mu minus omega d. See what happens. If we have the real part, we can actually build the imaginary part from it. The integral is known in the trade as the Hilbert transform. It's a bit difficult to calculate because it's an indefinite integral, but thankfully MATLAB would do it for you, and so would MATLAB. So if you only have a real part from any literature data, and the Navi, when he gets to EPR fitting, will actually only get the real part from the database. So bear this equation in mind. You will have to use it, or rather you will have to tell MATLAB to use it, which is a fair bit easier, to reconstruct your imaginary part for phasing before you actually fit those spectra. And these two things are also known in the trade as Cramer's chronic relations. They can be derived from different considerations from the ones that I have given. Different textbooks do it in a different way, but they are very useful in that they relate the real and the imaginary part of the response signal of any linear time invariant system. Okay. Right, moving on to very practical things. What would often come out of the spectrometer, and I guess people have been sitting at the spectrometer already with Marina by now, would be a signal which would have a distorted phase. We all know that wave functions are defined up to a complex phase, which is inconsequential in various observable calculations. But what is also true, and that is unrelated to the complex phase, is the detection circuitry of the spectrometer and the practicalities of giving a pulse to a system means that the signals that we get out of the spectrometer would often arrive multiplied by basically an arbitrary complex exponential. So the signals that we would have out would be f of t, maybe an oscillation of some kind, e I omega 0 t, an oscillation at a frequency omega 0, but it would have a complex phase, I phi, which is basically unpredictable. It is determined by spectrometer electronics, by the time it took you to start the detection, by all sorts of other things. And it might decay, kT, because of some relaxation. So, because of the properties of the exponentials, it just separates out, so e I omega 0 t minus kT. And the signals that we are interested in practice is this. It has a well-defined frequency, it has a well-defined decay rate, and we would ideally want to isolate that signal and put this to 1. And the process of putting it to 1 is called phasing, and this is what we will be busy doing now. But first of all, let us Fourier transform this signal. So it is an exponential with an oscillatory component and a decay component, which is real, as you can see, and so it's just a decay oscillator. is the real and the imaginary part. And let's do a Fourier transform. It's a trivial exercise, but it is highly instructive to just convince yourselves that the shapes of your signals, when they come out of the instrument, would have a Lorentzian shape. Right. F of omega is 1 over root 2 pi, Fourier transform, from 0 to infinity, because there was no signal before time 0, so we don't need to worry about that integral. It's 0 anyway. 0 to infinity, e I omega 0 t, the frequency term, minus kt, the decay term, e minus I omega, the Fourier transform term, d. Well, let's collect all of that under one exponential, and we know how to integrate the exponential. So, blah, blah, blah. Put it all together, we have three terms. There will be omega minus omega 0 in here. The integral of the exponential is the index coefficient. You divide it out, and you get the exponential out of it. We all know that. And the phase term should have been here in front. It doesn't depend on our integration variable because it's constant. So we inherit the phase term in I phi. We inherit the root 2 pi. But what we get is 1 over the total index of this exponential. So 1 over k plus I omega minus omega 3. Well, it's generally not a good practice to have imaginary numbers in denominators. So why don't we multiply this by k minus I omega minus omega 0? We have the difference of squares in the denominator, and the complex number will move to the numerator. So we basically divide and multiply by the complex conjugate of this. So it will be e I phi over root 2 pi, k minus I omega minus omega 0, and in the denominator we have k squared plus omega minus omega 0 squared. And now we can easily separate the real and the imaginary part of this. So let's do it. It will be the same phase multiplier, e I phi, root 2 pi, but now we've got two terms, the real and the imaginary. K over k squared plus omega minus omega squared minus I omega minus omega naught, k squared plus omega minus omega squared. Right. Well, if we plot this, it has this form, 1 over 1 plus omega squared. Yeah? It's a Lorentzian curve. It's a peak. Looks like this. And these are the peaks that are the signals in your NMR spectrum. It will be a peak at the frequency omega 0, and the half width at half height would be equal to k, if I remember it right. I may be wrong, but factor of pi or something like that in here. Whereas this, the imaginary part, is known in the trait as dispersion signal, because it is related to the amount of energy that the system just wastes, and it looks like this. It is considerably broader than this. It is also centered at omega 0, and this is the component that we would ideally want to eliminate. Now, see what happens if you multiply it by a complex number. Yeah, this is cosine phi plus I sine phi. If you multiply that in, there will be cosine times this, sine times this, sine times this, sine times this. When you collect the terms, you'll find that these two have mixed. You get linear combinations, and when they're mixed, the signal sort of looks like that, with a little dip and a little extra shoulder on the side. And what we properly want, because we want to quantify it and therefore integrate, is for the signal to be positive, because then the integral is actually the correct integral, whereas this is a combination of something that integrates to what we want and something that integrates to 0. And in the extreme, it would simply integrate to 0, or the integral will become unpredictable. So before that, also it's difficult. The maximum is shifted here relative to the omega naught, and so on. So we want to only keep the real component, because it is the component that contains our information. And so the process of doing that is called phasing. And let's say we have arrived and detected signal with a phase I phi. So we'll now need to find phi multiplied by E minus I phi, and that would actually phase the spectrum. Right. The way it's done is, you know, multiplication by a complex number is equivalent to rotation in the complex plane. So we simply need to find the backwards rotation. And in practice, this is done, well, usually just by eye. Automated phasing procedures look at the signal integral and try maximizing the signal integral as a function of the adjustment of the phase to theta. But really, for most practical purposes, it's sufficient to rotate the phase to a point where you've got the maximum intensity. And usually, if you do it by eye, the error doesn't exceed a couple of %, because it's very easy to judge when the point has been reached, because all the signals become symmetric. So real and the imaginary part we saw, it's given in equation 10 in your handout. So the phasing process consists in finding such a number phi and performing a transformation. Real part is f real that we have recorded times cosine phi plus f imaginary sine phi, and then the new imaginary is f real with minus sine phi plus f imaginary cosine phi. You see a rotation here. If we take a vector in the complex plane and rotate it by the angle phi, this is the transformation that we get. And we need to find such a phi as makes the spectrum look like the left part of figure 1 rather than the right part of figure 1. And this is an inevitable process. Every time you're recording an NMR spectrum, you will be faced with the problem of phasing. Now, it all would have been easy if it was just a single phase. Now, it so happens that phase distortions in the spectrometer are almost always frequency-dependent. And this simply is a transformation which would be the same for every frequency. But oftentimes what happens is this phase depends on where the signal is. If it's on the extreme right, the phase distortion has one phase, and if it's on the left, the phase distortion will have a different phase. And the reason for that is usually rooted in the modulation theorem. For Fourier transform, I will remind you what that is. We often have, if a pulse is given here, and the system starts evolving, there is a certain time here, this time interval, which is called the dead time, where we cannot detect the signal because of the various electronics taking time to switch on. And what this amounts to is effectively the displacement. This was our original 0 point, and this is our new 0 point. So a function f of t has been replaced with f of t minus t0, where t0 is the dead time of the spectrometer, so we've got a time shift. But from the modulation theorem in lecture 1, we know that the Fourier transform f plus of a time-shifted signal, t minus t0, is the Fourier transform of the original signal times e I omega t0 f plus f of t. Yeah, and this is frequency dependent. You see, t0 is a constant. This thing depends on the frequency omega, and so a phase would be linear in the frequency. It would depend on it. This is shown in figure 2. If you look at the top spectrum in figure 2, it is correctly phased. Every signal is a neat peak. If you look at the middle trace, this is uniform phase distortion across the entire spectrum, the same everywhere. And if you look at the bottom trace, this is an example of a linear phase distortion with different values of the complex phase at different parts of the spectrum. And when you do it on a spectrometer, every single one of you, particularly for things like carbon and fluorine spectroscopy, what you will necessarily find is you do have this linear phase correction. And you have to account for it. It's inevitable, it's natural, it's just a consequence of this little delta. So it's not something to be worried about. However, many spectrometers also allow you to tweak quadratic and higher terms in the phase. So what they say is your phase, which would be a function of the frequency, would be our static phase phi 0, plus the term that is linear in it, phi 1 omega, plus phi 2 omega squared, and so on, Taylor expansion. This, we have sensible physical grounds to expect. Yeah, this is always there, and this is the consequence of Froebel distribution. Beware, if you have to correct phases to quadratic order or higher, something is wrong. Normally, a spectrum that comes out of a valid procedure without hidden distortions or causes of those distortions should not need the quadratic terms in the phase corrected. If it does, then you're probably using shaved passes and you're probably not doing a good job of using them. So that's something to watch out for. Make sure that if you have extra correction terms in your phase, highly nonlinear ones, that you understand where they're coming from. Okay, so that's the phase, and it's maybe an example, certainly in the linear term, of a defect that one needs to correct. There are, in fact, a large number of these defects, and some of them are actually related to this dead time. It is often the case in fluorine spectroscopy that parts of the probe are made of Teflon, which is a fluorocarbon, and a fluorocarbon at a huge concentration, something like 100 moles per liter, and it has a signal. Signal decays extremely quickly, but because there's so much of it, I mean, 100 molar concentration compared to maybe a millimolar concentration of your sample, that's 5 orders of magnitude. The signal, however quickly it decays, will actually show up. Alternatively, if the probe is old, some capacitors will be arcing in it. Alternatively, if the cabling is not selected, there will be some radio frequency sloshing to and fro in there. Anyway, basic result is when you're recording your FID, and it looks reasonably well, but it will have a few initial spikes in here. The common result of this, if you just Fourier transform this signal, looks like this. You will have your spectrum, because the narrow lines are determined by the long-term behavior of the FID, but the baseline would look like this. So you have some signals here, and so on. So you'll have a collection of narrow signals on what is known in this rate as a rolling baseline. And the standard procedure, which is completely indefensible because it really makes subsequent quantification quite difficult, is to fit a polynomial through this and subtract it out. Now, this is okay for moderate cases, but fluorine in particular is quite notorious for this baseline will be severe. And if the signal-to-noise ratio isn't good, it's hard to decide which parts of the spectrum are actually signal-free. And so you might eliminate a particularly broad signal with this method as well. So, of course, the root cause is this. Yeah, something that decays really quickly at the beginning, and so causes these enormous broad signals, which we perceive as a baseline role. So, the proper solution is to eliminate this spike. And one of the procedures for eliminating this is known as linear prediction. It is fundamentally quite simple. We would say that because the signal is smooth, subsequent points of this signal may be thought of as dependent on the previous points of the signal. And because quantum mechanics involves linear equations, it is sensible to assume that it depends on the previous points in a linear way. So the future is a linear function of the past, as we know from quantum mechanics. So what we can say is that the nth point of the FID, so let's say we decided to reconstruct some future here, will be dependent on the previous points with some linear coefficients which we do not yet know. So a sum k from 1 to some point. Yeah? ak, and there's a previous point, fm plus 1 minus k. So this point here would be a linear function of a few previous points. Well, how do we find out what these coefficients are? This is what the rest of the signal is for. We can in principle start here at these points. The results we know. This would mean a system of equations for known results from known training set for unknown coefficients. So we can determine these coefficients from the part of the signals that we know about, but then use these coefficients to predict the signals that we do not know. So the first process is training, where the coefficients of the predictor are determined. And the second step is prediction, where they are used to reconstruct the missing. The procedure can be carried forward. For example, if you're not happy with the duration of the data that you actually recorded and you would like to have some more. Or it can be carried out backwards, in which case it would reconstruct the spike into something that the data properly predicts, which is some sort of smooth dependence. Result
stable in both directions?
It is. Time reversal. The result being that this baseline row disappears, you get beautiful straight baseline, and this is the only proper way of correcting baseline distortions that I know about. Do not fit it with polynomials. It is, let's say, ethically inappropriate. You should be doing it on grounds which are physically valid, rather than just empirical fitting of stuff. Okay, so the learning procedure is a training procedure. It's just a system of equations from L equals 1 to M on the training set. F M plus 1 will be K1 to M, K, F, M plus L plus K. And this is a system of linear equations for the coefficients AK. If there is exactly as many equations as there are coefficients, you can just solve it. If there are more equations than coefficients, you can use SVD to solve it in the least square sense. Anyway, you get these coefficients out, and you can then use it for prediction. And figure 5 in the handout gives an example of forward linear prediction. It's a single sinusoid for the basis for the training, with a bit of Gaussian random noise added to it in MATLAB. And then MATLAB simply has a function that performs linear prediction. A one-line command reconstructs the rest of the signal all the way to the decay. And now there I have 1,000 points that I know about, and I'm using 500 predictor coefficients. And you can see the quality of the prediction is quite good, even to 5 times the amount. And certainly, if we were missing just a few points here in the initial period, they are generally reconstructed really well. So use it to deal with baseline distortions. Use it to narrow the lines, because longer FID means narrower lines when you can afford that. It sometimes happens that you're just missing one thing here. In a two-dimensional spectrum, when you're recording the indirect dimension, it takes a lot of time. And in a 3D spectrum, it would take overnight. Some member of cleaning stuff came and started to hover under the spectrometer, and that particular trace became completely corrupted. And so this would allow you to correct for point defects in the indirect dimensions, so that the thing transforms to something sensible rather than a big bunch of noise, because just a single point being way off in the spectrum can completely correct the Fourier transform. So yeah, point defects can be done.
Do the coefficients depend on how you choose the training set?
Of course
you can use many points and training set.
Yes, of course they do. There are limitations. I mean, some data may not be a linear function of its last. This specifically assumes that it is. So it is an approximation. But the one that in magnetic resonance does work pretty well.
Do you have a criteria to understand if this assumption is good for particular data or not?
We don't. It's just spin systems very frequently behave in very linear ways. So long as the signal is a linear combination of decaying exponentials, this is in fact an exact solution. If it's not a linear combination of decaying exponentials, then this would be an approximation and it can indeed go dreadfully wrong. But it so happens that in NMR spectroscopy, to a pretty good accuracy, the time domain signal is a combination of decaying exponentials.
Then if you go to the origin of the signal, that must become an even function of time.
Who knows? I mean, it depends on where it starts from. So long as it continues being exponential, it should predict it okay.
How you choose the size of your memory?
The bigger the better. The biggest one you can realistically. So you usually use the entire trace as your training set. Right, so this is the case of point defects. Things can get even more dramatic. That is, whole chunks might be missing from the data, either unintentionally, if something happened, or by design. If you decided to sample your data non-uniformly to save time, but then the problem becomes that Fourier transform of non-uniformly sampled data isn't actually well defined. And effectively what you have is, compared to uniformly sampled data, chunks of it are simply missing. In that case, we need to resort to various nonlinear reconstruction procedures, and the best known one is simply known as retrofitting. That is, we can take a guess spectrum, inverse Fourier transform it, see whether it fits our time domain signal, compute the difference, takes the derivative of the square of that difference, and reconstruct the spectrum in the least square sense. Now, because the frequency domain spectra are usually sampled uniformly, and the time domain signal might be missing its significant chunks, such a reconstruction would not be unique. And so additional criteria such as smoothness or other properties are actually necessary in order to obtain a unique solution. And this is what the next chunk is about. So let's say we've got only pieces of time domain data, and so what we can try to do is to reconstruct our Fourier transform f of t as a minimum of the deviation from the time domain data that we do have. So argument of a minimum f omega, so we are fitting our spectrum of the following error function. It will be the norm of the difference of the time domain data that we do have from the inverse Fourier transform of our trial spectrum. F minus f of omega, normal square. So we guess some spectrum, compute the time signal, subtract it from the real time signal, see if there's any difference. If there is a lot of difference, we try reducing that difference by varying this f of omega, and we iterate until the difference gets smaller and smaller and smaller and smaller, and finally, hopefully, it becomes smaller than the precision we have in our data, in which case we sort of have solved the problem, although the solution might not be unique. Now, that non-uniqueness requires extra care. We would normally like to avoid some really erratic broken shapes, which might be valid solutions but would be physically nonsensical. And this is the reason for introduction of what's called a regularization function f of omega. And R has an interesting definition. It is large if the spectrum is not what we want, and it is small if the spectrum is what we want, which is a very broad definition, and so people often constrain it to what's called a Tikhonov regularization, which would simply apply a linear operator to it. And one of the frequently encountered criteria is that the reconstructed spectrum should be smooth. And it's rather difficult to define smooth, although we know that physical reality does not have discontinuities. Yeah, if you take a system that looks like it has a drop, and look at it really, really, really closely, you'll see that the drop is actually smooth. So no discontinuities in physical reality, and so it is often the case that people choose the following function. K times the norm squared of the derivative. Of omega. See what this does. If f is very erratic, the derivative will be large, because the rate of change is big. Then the norm, which is just the length of the vector in the corresponding space, would also be large. If f is smooth, then the derivatives are small, because the rate of change is small. The norm is small, and so this particular term is large for very noisy functions, and it is small for smooth functions. And so it is often imposed as an additional criterion in these reconstruction methods to try and find a good solution, but in the class of relatively smooth functions. So, yeah, and that's about it really. Tikhonov regularization on the derivative, this is called. And this procedure is just numerically carried through. And on a uniformly sampled data sets, this is the current modus operandi of how Fourier transform is computed. An alternative, which also has been studied rather a lot to this regularization, comes from mathematical statistics. If you look at a spectrum, it has a collection of peaks, and a well-phased spectrum would be positive everywhere. So we can, in principle, treat this as a probability distribution. So let this be a frequency, and this be a probability of that frequency, in which case an NMR spectrum is a density of transitions, density of allowed transitions, and so it could be thought of as a probability distribution for transitions in the same sense as a Gaussian, for example, is a probability distribution for some random events. Now, probabilities are well researched, and they've got a number of interesting properties. One such property is known as entropy. S is minus A, a number, just user selectable really, from n equals 1 to n, where this is the number of distinct frequencies we have in here. Pn is the value of the spectrum at nth point, and then logarithm Pn. Now we are edging into philosophy here, but the understandable explanation of this rather strange contraption is it gives us the measure of statistical uncertainty that is inherent in this distribution. That is to say, if we choose this as a regularization parameter, then what it will bias us towards is the solutions that give us the least amount of information. And the philosophy goes that if we choose the solution that has the least possible amount of information, then it cannot possibly give us any incorrect information. It would only contain such information as is strictly consistent with our data, but no more. So this philosophical argument is the core of the maximum entropy method. So we find something that is a solution to this problem. However, it also maximizes the entropy of that solution, and therefore minimizes the information content. And so the solution with the smallest information content is the solution that we probably want in an imposed problem, because it's better to not have information than to have wrong information, or at least so the philosophy goes. And I will say no more about this method. It tends to polarize opinion rather a lot as to whether it is even working, and when it's working, whether it is actually useful and not misleading. But it's a part of NMR history that you should know about. Try it if you want. MATLAB will again easily do it for you. It's a one-liner, and there are multiple software packages out there that will do such processing for incomplete data. Of course, if your time domain data is complete and has a good signal to noise, then you don't have any reason to use it, because your signals are already there. It's when the data is noisy and incomplete that these things start to come into play. I've put some literature about maths and references for it, but more detail about it. Okay, that's it for today, and into quantum mechanics from the next lecture.